So I hope you all enjoyed a little AC/DC, especially since we're going to be talking about currents today, and AC/DC are two different types of currents. But first we're going to talk about how is current produced. So over here we have something with low potential and something with high potential. We know from our potential difference stuff that the stuff with high potential wants to go down here to the low potential. So when a high potential is connected by a conductive material to a low potential, that is how current is produced. Here's our conductive material right here, this piece of wire, right, copper or something. And then it wants to go from high potential to low potential and creates a current, a flow. See how they do that? So a flow of electrons is called the electric current. Currents, we have the symbol I. I stands for current. Don't ask me why, it's probably some Latin thing. Which equals charge per time. So charge per time gives you current. And if charge is in coulombs and time is in seconds, current is going to be in coulombs per second, which we're going to give its own special name here in a minute, which is amperes. So when the potentials are equal, the current stops flowing. So if these potentials become equal, then there's going to be no more current to flow. So to increase the potential of the electrons, an electron pump must convert, do work, another form of energy into electric potential energy. So we have an electron pump here that does work. It keeps these electrons flowing. Some pump examples: a voltaic or a galvanic cell, it's a dry cell. Several cells connected, which we know as a battery. Photovoltaic cells, which are solar cells, or a generator like your parents might have in the house in case the electricity goes off in our lovely New England winters. There are two types of currents. We have direct current, DC, the flow of electrons only in one direction. Batteries are good examples of things that produce direct currents. You see the electrons only go in one direction. They're both going, or it's always going this way. You can also have the AC, the alternating current, flow of electrons at first in one direction and then in another direction. So you can see these electrons, they go back and forth, alternating current. So these same electrons just wiggle back and forth the whole time. An example of this would be a generator in your house. It just shifts electrons back and forth. It's much more efficient, thank you Nikola Tesla, than direct current. You're a bad man, Thomas Edison. Tesla advocated the alternating currents, Edison the direct, and unfortunately direct current won, even though it's a lot less efficient than alternating current. And alternating current in your house is about 60 hertz. So hertz, remember, is something per second, so 60 electrons per second. So what affects the flow of currents? The potential difference affects the flow of currents. Resistance, or slowing or reducing of the flow of current. Anything that reduces or slows it, we call resistance. Makes sense. Resistance depends on the material, the length of the material, and the cross-sectional area of the material through which the current is moving. We have this ugly little formula right here. R, resistance, equals rho times L divided by A. Rho is the resistivity. It's like a specific to each type of material. L is the length of the material, and A is the cross-sectional area of the material. And we have this guy called Ohm. Kind of sounds very Buddhist. Ohm. But he has this law, and it says the ratio of V over I, voltage over current, is a constant, where V is the voltage, which I just said, and I is the current. And R is the resistance of the piece of material in question. The units are ohms, and we give the symbol of an omega. It's a Greek omega symbol. And the units are volts per amp. That's what an ohm equals, because we have V over I. So V is measured in volts, I in amps, volts per amp. We call an ohm. So Ohm's law states resistance equals voltage divided by current, or R equals V over I. Remember, this R is always going to be a constant for whatever piece of material we're talking about. A volt's measure of electrical pressure and is named after some Italian dude. The energy each electron has is called its electric potential. Electric potential is commonly referred to as voltage. And we use a voltmeter to measure voltage. The symbol for this unit is V. That's probably all review stuff except for voltmeter used to measure voltage. Electric current is the quantity of electricity going by a point in a circuit. How much charge is going by a specific point in a specific amount of time. Current is measured with an ammeter. The units for current are amps, so we measure it with an ammeter. The unit to measure electric current is the ampere, yada yada, named after some French dude. And resistance. Molecules of all types of conductors impede or resist or slow down the flow of electrons to some extent. The ability to impede the flow of electrons in conductors is called electrical resistance, simplified by R, and its units are ohms. Factors that affect the resistance of wires: the thickness of the wire, the length of the wire, the material the wire is made of, and the temperature of the wire. If we change the temperature or something, to me, they're more or less resistive. So Ohm's law again, this guy George Ohm. V equals IR, I equals V over R equals V over I. All just Ohm's law in different ways, solving for different things for each one of those. Current is directly proportional to voltage. Therefore, if we increase the voltage, we also increase the current, directly proportional. The current is inversely proportional to resistance. Therefore, as resistance increases, current's going to decrease. Remember, inversely, whatever you do to one, you do the opposite to the other. Directly, whatever you do to one, you do the same thing to the other. So some questions. What is the formula for Ohm's law? V equals I over R. I equals V over R. Or R equals V over I. Either one of those will work there. And if a water heater has a voltage drop of 240 volts and a resistance of 12.8 ohms, what is the current? So we use the Ohm's law to solve for I equals V over R. Plug in our voltage and our resistance, 240 divided by 12.8, and we get 18.75 amps. So therefore, the water heater has a current of 18.75 amps. When we're talking about electricity, we can also talk about power. When there is current I in a circuit and as a result of a voltage, the electric power delivered to the circuit is given by this equation. Power equals current times voltage, or P equals I times V. The units are watts, named after another dude named James Watt. And it's an amp times a volt. Or we also give this as a joule over seconds. You may notice in your house that some of your electrical devices become hot when provided with too much power. Toasters, irons, space heaters, heating elements in electric stoves, and incandescent light bulbs. In such cases, it is possible to obtain two equivalent power equations. You have P equals I squared over R. And where does that come from? Well, if we go back to this guy, and P equals I times V, and we know V equals I R. I should probably do this on the next slide. Let me go back there. And where was I? Yes, V equals I R. We plug V equals IR in for V over here. Yeah, I like it on the side better. So we plug this V in here. We get I times I R, which is I squared R. I squared R. Same thing here, except for solving for, instead of replacing the V, we replace the I. And we know from Ohm's law that I equals V over R. So we have power equals IV, or since we know I equals V over R, we get V squared over R. That's how we get our second equation. So when electric energy is transferred into thermal energy in a resistor, the increase in thermal energy is Q, which you remember from thermodynamics, Q equals MC delta T. It also equals I squared R times T. So I think in your book they might use E for this. or Q, one of either or. The units here are kilowatt hours or joules. And we're also going to talk about electric circuits. An electric circuit is a closed loop. You can't have a circuit if you don't close the loop. Basic circuits consist of three things: an electron pump or a battery, a device that reduces potential, a user, in this case a light bulb. A light bulb is our user, and conducting connections, which are the wires. They conduct the electricity. They allow the electrons to flow. So that's how we get our current. You have direct current circuits, like I already said, circuit, closed loop in which current can flow. Basic simple circuits, voltage source, voltage users, and conducting connections. So here's our battery, conducting connections, user, and then we can also measure stuff here with a voltmeter and an ammeter. So diagrams for electric circuits, you can describe them in words. You can use photographs or drawings, or you can use schematics. We're going to get a lot of practice drawing schematics. Just a simplified diagram of this stuff. It's pretty easy though. Simplified diagram for this guy would look something like this. Here's your battery, here's your resistor or your user. You connect your voltmeter in series and your ammeter in parallel. We'll talk about series and parallel though in a little bit. So here is some basic symbols for when we're doing schematics. Conductor is just the wire, we draw it straight. Switch, we kind of draw like this, that way you can close the switch to complete the loop. Fuses get a nice wavy line. Capacitor, I think in your book it might use just a straight line here, so two straight lines of equal length. Resistor, you do a jagged line, and a potentiometer, jagged line with this arrow over it, and you can actually like change the resistance. So something like light bulbs in your house that you can dim, like would be an example of a potentiometer. Some other basic symbols: ground wire. If we have two wires crossing, we have connection there, so we have to draw a little dot. Batteries, you can either draw just these first two, a big line and a little line, or a series of big line, little line, big line, little line, big line, little line. Big line is always positive, little line is always negative. Voltmeter, circle with a V. Ammeter, circle with an A. Generators look like this. You can just use this chart to refer to when you're drawing schematics. So the first thing you want to do when you're drawing schematics is draw the symbol for the battery and always indicate which side's plus and which side's negative. You draw a wire from the positive terminal to the voltage user or the resistor and draw its symbol in there. At the point where there are two current paths, you draw a connection symbol and follow one of the paths. And we turn to the second path and draw it to its user and can continue until the path joins. And you follow a nice complete path until you reach the negative terminal. You always check your work. And always remember that we connect ammeters in series and voltmeters in parallel. So if I wanted to draw a schematic for this guy, this one would be pretty easy. First we draw on our battery, long side, short side. Long side's positive, short side's negative. We draw our wires around. Oh, we hit our first light bulb. So it's a resistor or a user. Nice straight conducting wire till we hit our second light bulb. Nice jagged line. Then we follow it around. Then we draw in our nice little switch that we can close to complete this path. So while the switch is open, free electrons, the conducting electrons, are always moving randomly. So they just bounce wherever the hell they want. And these speeds are, pretty high. They're on the order of 10 to the 6 meters per second. And there's no net movement. So this guy might start here, but he's going to end up back right here. So there's no net movement across the section of wire. So when we close the circuit, all this random stuff becomes less random and starts to go this way because an electric field is produced. And since an electric field is produced and this side is positive, our little negative electrons here want to go that way, from higher potential to lower potential. So an electric field is established instantaneously, almost at the speed of light. And speed of light, if we remember, is 3 × 10⁸ meters per second. The free electrons, while still randomly moving, they start to drift due to the electric field, resulting in a flow of charge, resulting in a current. So in the average at which they drift is about 0.01 centimeters per second. Not very fast, but there's like so many electrons in there, it's ridiculous. So that's why we get a nice current that flows. So electrons flow in one net direction. So the electrons, they want to go from low potential to high potential. Actually, these guys are backwards. They should go this way. They want to go from high potential to low potential. So they want to go this way. Quick question. Why is the bird on the wire safe? Why? Because he's not part of like the series. He's not grounded to anything. So poor little birdie, he doesn't die. He stays alive. Even though I'm going to draw little X's over his eyes like he's dead. Why do electricians work with one hand behind their back? Think about it for a second. Because if electrons accidentally were grabbing a wire with one hand and then grabbed another wire with a second hand, they would complete a loop, and that current would flow through their bodies, causing them great harm, maybe even death, which would suck. Another question, why is the ground prong longer than the other two on a plug? This is because the ground will stay grounded longer than the actual two wires that are producing electricity. So if we keep the ground in there longer, we can break the circuit before the ground is out. That way the ground is still transferring whatever left or whatever net charge is still left back into the ground and making it safe for all of us. That's it. Thank you. Adios. Adieu. Auf Wiedersehen.